So this is, I think the first two parts of the problem are pretty simple, right? Okay, let's think about it. I vote for somebody. Okay, somebody killed. So let's think of cancellation. See, there is a vote for X. I look at the first vote. Okay, this is for X. Now I look at the second vote. That's for somebody else. Then I can cancel that vote and say, okay, right now there is no leader. Okay, suppose there are only two people. The first vote goes to one person. If the second vote goes to a different person, then there is no leader, right? So one person should accumulate votes. One person should accumulate votes. See, suppose, okay, let's think about it. Assume that the first person is the leader. Assume that the first person is the leader. Okay. So the first person gets, let's say the first vote is for some other person. Actual leader is first person, but first person vote is actually for somebody else. So let us say 10 got the first vote. Now second, third, fourth, second person voted for first. I can cancel out one vote from 10's vote, because now 10 got one vote, somebody else got one vote. That somebody else you don't have to count, because 10's vote is cancelled by that somebody. See, if you are a leader, you got say 100 votes. After cancellation, still you should be left with some vote. Whatever be the sequence of cancellations that happens to your vote, right? You should still emerge as a leader. So basically, I can pair up votes in such a way that they cancel each other, and finally somebody will have more votes than what. See, if two people get one vote each, we can remove those votes outside and say that, okay, I will look at the problem. Assume that there is a leader. See, two people, if there is a vote for one person, there is vote for another person, I can think of these two votes killing each other, because this doesn't count to the election of the leader. If one of the votes is for the leader should will have more votes to come, so there is no problem. So you try to pair up votes. You try to pair up votes, and when X gets a vote and when you see the next vote it is for Y, if then X is not equal to Y, then you can just kill your count so far. If it is for X itself, of course you should increment. Okay, because X has got two votes now. Accumulation of votes, somebody gets accumulation of votes despite cancellation, one needs to count. Okay, this is the strategy. Now think about this like this. Assume for the time being that there is a leader. That means, see, there are two cases possible, right? The array, there is nobody is actually a leader. That's one possibility. The other possibility is that there is a leader. Assume for the time being that there is a leader. Now think of the algorithm. Why should you check this? A random person doesn't work unless you want to do something in probabilistic.
The probability of
No, I want right now the model is, we are assuming you are not solving the problem on a probabilistic polynomial linear time. So randomness doesn't pay off here. See, this is actually, there is nothing computer science here. You can, if you are from some other background also, you can think of it as people voting for, just as a chairman you are asking to the first person. See, if I am the chairperson, I am trying to gather the votes, I go and ask the first person, whom are you voting for? She says somebody. I ask, whom are you voting for? She votes for somebody. If these are different, I will cancel, otherwise I will increment her vote to 2. See, if both of them vote for the same person, I will increment the vote, right? So this way, if at any point of time somebody gets more than n by 2, immediately I know. Okay, I have been given enough clue now. So I will leave this problem here. We will solve this we will think about it later. Okay. Let's come back. We will solve this problem later after the tea break. When is our tea break? 3:30. So we will think of solving the problem after the break. But the moral of the story, listen, let's come back to this. I think, okay, people are still solving the problem. Now just come back, we will think of solving the problem later, because there is enough time. So we will have another, see after some lecture, anyway the break is required because lecture is boring. But lecture cannot be avoided also. I need to define what NP is, right? So lecture will be a necessary evil. So we will start with the lecture for some time. Once I see that you are tired, we will come back to the problem which is more interesting. Okay. So what is the moral of the story here? The same issue comes here, right? Solving the problem is harder. Verifying whether X is a leader is easy. So now let us think of a polynomial time verifier for a language. So suppose given a problem, decision problem L. So when should we say that L is polynomial time verifiable? What should be a reasonable definition for this? See, there are given, so on input, a verification algorithm A for L must have what all inputs? Must take at input what? See, the input has to be given, right? Additionally, what is to be given? A candidate. A candidate has also to be given. This candidate is sometimes called a certificate, sometimes called a proof, etc. So a verification algorithm for L takes as input one, a problem instance, two, a candidate solution. See, we have seen two examples, right? So the notion is clear. See, the problem instance we have seen in each of the two questions. The first part was about solving the verification problem, where the problem instance and a candidate solution is given, and you want to verify whether the candidate instance is a solution to the problem. In the second part, only the problem instance is given. You are not given the candidate. Okay. So a verification algorithm for a problem takes as input a problem instance and a candidate solution. And what is the verification algorithm supposed to do? Determine whether, okay. So there are, see, now when we formulated, there should be some completeness in the sense, okay, let's see, what are the issues? Let's think of this problem in a different way. Instead of, see, there is a problem of checking whether a person is coming to log in, right? A person is coming to log in. You want to check whether the person is a legitimate user. This is the password, the login security problem, right? When a user tries to log into a system, you need to decide whether the user is a legitimate user. This is the problem to solve. This is typically solved using a certificate candidate. What is that certificate? You are asked to enter a password, authentication, so some kind of authentication certificate you need to enter to the system, so that the system verifies with the help of the certificate whether you are inside or not. So, whether you are inside or not is something like X is in L or not. See, all users who are valid users are in the language, all users who are not valid users are not in L. So, it is just like a language decision problem. Now, what is the requirement? What is the requirement on the verifier? Intuitively, if you are writing down the specification of the verifier or of the security system, what are you going to write down? If a valid user comes, if the valid user comes, you write down the wrong password, are you in? No. So, the system does not guarantee, in that case the password is irrelevant, right? Isn't it? The password comes into, see how does the password help? See, there is some kind of a convention which associates with each valid user a password for that user or certificate for the user, with the help of which this guy can verify whether this person should go in or not. Is that clear? So, for every legitimate user, there is a password which if you enter correctly along with the username, you should get in. If the legitimate user comes with the wrong password, the system is not expected or required to let you in. See, for some reason, if the system is intelligent even to identify you despite the password correctly, system is brilliant, but that is not a requirement of the verifier. The verifier's duty is, if a legitimate user comes, see, for each legitimate user there is a valid password, that should be there, otherwise the system will fail to verify even legitimate users. So, for every legitimate user, you have a valid password with which if the user comes, the system should accept this person. If a legitimate user comes with the wrong password, the system has no responsibility to accept the user. If an illegitimate user comes with whatever password, the security system should reject. This is the requirement. So, let us write down this requirement from an algorithmic point of view. Let us write down this requirement from an algorithmic perspective. Where did I put the chalk? Okay. So, language is polynomial time verifiable . So, you have no objection with both sides, right? A verification algorithm A for language L takes as input. So let's call a problem instance X in sigma star, which is your instance. Let's also call the Y element of sigma star, which is your password. So, you have two input system. I am modeling it as a two input system, the username and password. Okay. Username is you want to check whether input belongs to L or not, right? X belongs to L or not. See, a computational problem, you are given given a number, you want to check whether it is prime or not. So, you are given a number. Now, here a prime number is supposed to come with a certificate, a password for primality, and if the prime number comes with the correct password for primality, this guy is allowed. The verification algorithm accepts this guy is prime. If the prime number comes with the wrong certificate, this guy is kicked out. That is fine. And if a non-prime composite number comes, whatever be the password that is given, the system should not let you in. Okay, is this clear? That's what a prime verifier should do, something like this. So you have a problem instance, input to the problem, and you need to supply a certificate to the verifier. So for each x in sigma star, what should be the behavior of A? If x belongs 12, this means what? X belongs 12 means x is a prime number or x is a valid user. It's all same the analogy. Mathematically stated, x is an input that should be accepted, that is in your decision, in your language. See, a decision problem means for each input there is a decision to make, yes or no. If x is a yes instance, then what should be there? Then there should be a certificate which exists. It's for x to find out the password or set the password, that's not the verifier's job. But if x belongs 12, then there is an appropriate password. There is an appropriate password such that the algorithm, if you supply x along with the password, this guy will return 1, accept. Is this very clear? If the input, if you give the input, the problem instance along with the right candidate, your algorithm should return 1. If the problem instance is provided with the wrong candidate, even a problem instance, yes instance is provided with the wrong candidate, it should return, the verifier should return 0. Okay, 0, it's not bound to accept. It may return 1, it's not a problem. But the important part is, if x is not in L, then what is the requirement? You should not be able to cheat the verifier, cheat the security system. That means what? For all y, A x y equal to 0. So you should, there is one catch in this notation, for every there exists. See this there exists y, for if for x in L there is a corresponding y, so this y depends on x. One, it's not every user has the same password, y depends on the user, right? So y is a function of x, but that's an implicit function, I don't care. Each user can give a password which is accepting, each valid user. If an invalid user, if an invalid x comes, whatever be the proof given, verifier should reject. Now don't go and tell somewhere valid user, etc., etc. This is for analogy to understand. Okay, the formal notion is, if an input x in sigma star is given, if x belongs 12, then there must exist a y which, if you give the verifier should accept. And if x doesn't belong 12, then for every verifier, every certificate, whatever you supply as the second input, A should reject. This is the purpose of a verifier. Now let's see. Let's come back to this leader election problem. Now what is the instance of the leader election problem? So I will put this as, we want to put it as a decision problem. So now what is the decision problem associated with the leader election problem? Is there a leader for the group? Is there a leader for the group? Okay. Is your verifying algorithm, is your verification algorithm adaptable to solve this problem? What is the requirement? If the vote, see, you are given the votes, number of people, votes, all those things. That's what is given to you. What is your algorithm supposed to return? Pardon? Is there, what does algorithm return? It returns 1 if there is a leader. It should return 0 if there is no leader. How will you do this? How do you design a verifier for this? You have already designed a verifier. What is that verifier doing? What should the verifier do? No. Is your verifier good enough for that? Now it is not, right? Because it checks for one, that's enough. But the question is, you may not have a leader. Okay, so now that you have designed an algorithm, can you adapt that algorithm to become a verifier for this problem, leader election problem? So let's define the decision problem L. So now let's look at the language leader election problem. What is the instance, what is your language leader election problem's language? What are the inputs? Number of elements, there is an n, right? There is an n, an array of n elements. Array is actually votes, right? Votes is a array of n elements. This is your input, such that there is a leader this is your problem instance, correct? See, what is your input to the problem? This is your input instance, right? You are given an n and an array of votes. You want to check whether there is a leader in the system, correct? Is the problem clear? So this is your x, typical value of x. Now what is algorithm supposed to return? If x has a leader, then you should return 1. If x has no leader, return 0. But now, okay, there is a little bit of confusion because this x is not the x in the, this is different. This is the problem instance x. So let us call the candidate y instead of x. I have written candidate is, okay. Now, this is the original problem. If an algorithm for solving the problem, if you are to design a algorithm for solving the problem, these are the inputs. But if you are designing an algorithm for verifying this, what are the inputs? There is a second input. You make a system with, you modify, create an algorithm with one more input. Okay. So the verifier for this will be, so the verifier so verifier how, if you are designing one, it should have, apart from this input, one more input. That's the first thing. A verifier should have this as the input along with one more input, which is the candidate. So algorithm must have what are the inputs? Int n, there is an input integer n, then there is an array a, these are the standard inputs to the problem, and then candidate's number, right? Let's call this y. And then you have some code. This is how the verifier would look like. Okay. And what is your algorithm supposed to do? The algorithm should check whether y is a leader. Okay. Now, with that you have already written, right? Is this algorithm a valid verifier for the problem? Is this algorithm a valid verifier for the problem? Yes, let us try to prove. So, what is to be proved? So, let us call this x. Given an n and an array, we want to show that. So, okay, so I have not written any algorithm here. I assume that you have already written the algorithm for checking whether y is a leader for the system. That you have already done. This is what I assume, right? Everybody has done this? Okay, so you have written an algorithm which looks like this. My question is, will this algorithm satisfy, okay, what is your algorithm doing? Checking whether y is a leader. If y is a leader in n comparisons, right? If y is a leader, you will return 1. If y is not the leader, you will return 0. This is what your algorithm is doing. My question is this a valid verifier for this particular problem? For the leader election problem. Let us see. So, this is the definition. If x belongs to L, then there should exist a y. If x belongs to L, that means output of x is actually should be 1, then there should be a y such that your algorithm should return 1. If x has no leader, whatever you supply as y, your algorithm should return 0. Will your algorithm satisfy this requirement? How many feel it is yes? How many feel it is no? You have to introduce some y because, yes, the password, that is your password. But in this case, no, candidate is not x. See, candidate is y. This is your candidate. Okay, if you want to change names, let us, I have already used x and, okay, x and y. So, this is algorithm. This is the content of this algorithm you have already written. The content of this algorithm you have already written. What I want to study is, does this algorithm qualify to be called a verifier for the leader election problem? So, let us come back to the definition.
In the definition of verifier, there is a password.
In the definition of the verifier, for each x for which the answer is L, it says there must be a y, password or candidate or something, such that the verifier returns y. And for each x not in, that means each instance where there is no leader, whatever you supply as y, the answer should be 0. Now, the algorithm you have written is something fixed. Is this qualifying this requirement? That is the question. Yes. Yeah, let us see. Why?
Because if there is any leader,
Yeah, so if there is a leader, then no, if there is a leader, are you always sure that this thing will return 1?
no, this not should be written 1. If there is a leader, x will return 1. That
No, if there is a leader, your x is this. Okay.
if it is true,
If there is a leader, yeah.
then the y will be compared with that. Leader will be checked with that.
No, see, this is your x. This is different from the x in the problem sheet. I repeat, this x is different from the x in the problem sheet. The x in the problem sheet is y now. The x is the candidate in the problem sheet, that is called y because I have given x called x somebody else.
Yes. Sir, in this verifiable definition, I am using x only here. Transport.
Now, if you are talking about the candidate, okay, in that case I am going to change this definition. Okay, if let's call this some alpha. I want to check whether alpha is in L or not, let's say, so that I can make x, y, etc., etc. So if alpha is in L, there exists an x such that A alpha x, this is just change of variables, nothing more than that. If alpha is not in L, then there exists for every x, A alpha x should be equal to 0, and this will be called my alpha. Now I am safe, I can call this alpha and this x, and that clears the confusion.
If alpha belongs to L,
What is the condition for alpha belonging to L?
if alpha belongs
No, when do you say that alpha belongs to L? If there is a leader for the set. Yes.
if alpha belongs to L, that is if there is a leader, we'll accept only if that shows a certificate.
Yeah, or no, the question is, can you always say that this algorithm can be made to return 1 by applying a certificate? Is it always true that there is a way of making the algorithm return 1 when alpha is in L? Is it always possible? That's the point. If alpha has a leader, then you have to ask the question, is it always possible to make the algorithm return 1? Is it possible? Yes. See, if alpha is in L, question is, does there exist an x such that A alpha x equal to 1? This is the question. If alpha belongs to L, can you always guarantee that there exists an x?
That X, that's a big condition. What's the certificate should be here?
That's the question.
No,
The algorithm will decide.
one more case is that if alpha belongs to L, need not imply A alpha x equal to 1.
No.
Suppose alpha belongs to L, but to show the output equal to 1, we want a x. So one more case is there, alpha belongs to L, but no x we have.
That's possible. If alpha belongs to L, if no x is possible, if for all x still you give 1, then even if alpha is 1, there is a situation where, see, I am a legitimate user. This is something like that. I am a legitimate user, but I don't have a valid password. If that happens, then you say this verifier doesn't work. Then this verifier is not working for the, see, for every valid user, there must be a password. Only then this guy qualifies to be called a verifier. That's the guaranteed completeness part of the definition. So this says that this is called completeness. This says that if x belongs to L, that means every valid user has a way of getting into the system. Every valid user should have a way of logging in.
One example was prime number checking.
No, this is already an example.
Already example, but I'm checking. There we have a prime number is come, prime number is given. We should accept. But what's supposed to be the certificate there?
I didn't say that prime numbers are easily verifiable.
Not easily.
So primality is not easily verifiable. As a matter of fact, primality is verifiable. But then that's a theorem by somebody's name. So the certificate is, you need some algebra number theory to get that Pratt's theorem, it's called. But the compositeness is easy.
I don't have any idea about what kind of thing will be this certificate.
Yeah, let's look at this particular problem. Okay, if you want to find a certificate for, let's think of it, forget about primality, look at its complement problem. You want to check whether a number is composite. What is a good certificate for compositeness?
Divisible by some number.
Some factor. One factor is a certificate for compositeness, right? So their certificate is clear, right? If the number is composite, you always have a factor. If the number is not composite, you never have a factor.
So actually mathematics
You need to show that, no, you need to ensure that a certificate always exists. Only then a verifier can be designed. See, if you want to design a verifier, you have to find and design some way of ensuring that every valid alpha has a certificate.
So actually our decision problem is one thing we have, whether it belongs to something or not.
Okay. So the question is whether this belongs to, this is a set system with leader or not. That is your problem. And I want to verify whether this system has a leader or not.
Something belongs to
See, let's be very concrete instead of being abstract. I want to check whether this system has a leader or not. Why should you want abstract?
certificates.
No. Is the problem in the first place clear? Is the problem in the first place clear? No. Is the problem clear? Is the problem clear? I am given this. I want to check whether this guy has a leader or not. This is my problem. I want to design a verifier for this. No. Let's not start designing the verifier. Let's fix the specification of the verifier. I want to design a verifier. Instead of writing down the verifier, let's try to specification. Let's get the specification right. What is the verifier supposed to do? What are the inputs to the verifier? What are the inputs to a verifier for this language? The verifier should have two things. One is this itself. The second thing you are free to decide. The second one you are free to design, and you have to design a verifier algorithm which does this verification. Okay. What's going on? Okay. So, I want to design a verification algorithm. The verification, any verification algorithms, first input is the problem instances itself. Verification input algorithm is free to ask for one more input. Okay, so that is my allowance. When I am asked to design not a solution for the problem, only a verification for the problem. So I can design an algorithm which not only asks you for the problem instance, but also asks you to give a certificate along with the problem instance. Is that clear? So, for this problem, what is the certificate I can ask you for? Or what is the proof or password I can ask you for this particular problem?
I have more than n by 2 people.
Now, what is the certificate? The person's number, the lead. See, if there is a leader, you give. I can ask. See, as a verifier, I can ask. When you bring the problem instance, you also bring me a candidate leader. See, when you bring the problem instance alpha, you bring me also a candidate leader X. Now I will do the verification. Okay. And that is what you have done here, right? What your algorithm is doing is, you are checking whether X is actually a leader for the system. This program you have already written. Now my question is that enough as a verifier for this language, is that enough? See, we have designed an algorithm already. Is it a valid verifier for the language? This is my question. So let us look at the definition. See, whenever there is a question, is this a valid verifier for the language? Let's look at the definition. What is the requirement? If this alpha has a leader, then what is the requirement? There should exist an X such that your algorithm returns what? Will your algorithm have such an X? Yes. What is that X? The leader, the number of the leader. So condition number 1 is satisfied by your algorithm. Will your algorithm satisfy condition number 2? Yes, because if alpha doesn't get n by 2 votes, you will send 0, right? So that condition is also satisfied. That means you have already designed a verifier for leader election problem. Now this is a point you have to be absolutely clear about, that you have designed a verifier for the leader election problem. Take a minute to digest this. Now I will go around. This is one of the most central concepts in theoretical computer science or algorithms. So this is a little involved, but it's just a matter of mastering it for once in a lifetime. You will never go wrong with it. The notion of a verifier. A language is verifiable if for each problem instance, okay, there exists an algorithm. If a language is verifiable, if there exists an algorithm which is a verifier, such that for each problem instance, if the answer is yes, you can also supply a second input which makes the verifier accept. And if the instance is a no instance, whatever certificate you supply, the algorithm should reject. Now in this case, are you convinced that your algorithm does satisfy these two constraints? Are you convinced that your algorithm satisfies? Now I just want to see how many people are clear about this. So this number is not very large, so I will try to address the remaining.
That composite problem, same way, one problem and its
Okay, let's write it down. This might be easier perhaps than this, so I will write it down. So, okay, I'll just explain this. Listen. Please listen. Please listen. Please listen. See, why is this a verifier? The reason is, if this set has a leader, your algorithm is what is your algorithm doing? It simply checks whether x has greater than n by 2 words. So now let's look at this. If alpha belongs to L, that means alpha does have a leader, right? That means it's an S instance. See, if alpha is a S instance to the language, then there exists an X. What is that X? The leader. Okay, there exists an X which makes your algorithm run and return value 1. So when the answer is yes, there exists an X which makes the algorithm return 1. That's condition number 1. If the answer is no, if alpha doesn't have a leader, whatever X you give here, you will check and only then answer, right? So whatever X the other guy gives, your algorithm will always return 0. So this, your algorithm actually satisfies all the conditions stipulated for a verifier for the leader election problem. Remember, if alpha belongs to L, it doesn't mean that for any X, your algorithm should, no, then the certificate is not being used, right? So the requirement is, if alpha belongs to L, there is a way of satisfying your algorithm and return 1. So what I want is you be convinced that the algorithm you have designed is a successful verifier for the leader election problem. Is that clear? Is it clear to more people now? So let's take another example which we have been talking about. So given so I want to check whether a given number is composite. I want to check whether a given number is composite. Can you design a verifier for that? So the moment this question is asked, you have to think of having an algorithm. So verifier is an algorithm which returns true or false. In fact, a Boolean value is returned one is the input x, you also have another input, it turns out to be an integer y. How should the verifier look like? What should your verifier for compositeness be? So this is your language. What should the verifier for compositeness be? You need to do some, you need to check whether y is not equal to 1 and y is less than. So little bit of work is there, but see, you should not let your verifier be cheated by some. What is your requirement of the verifier? If x is prime, what happened? Check. Fine. Oh. Which one is, yeah, I think correct. Okay. So now what should be the verifier doing here?
Verifier has input, same input as this and one
Extra input. And what is the requirement? What is that? Okay. Don't start running the verifier. Let's write down the SRS, system requirement specification. What is the requirement? If x is composite, if for each composite number there must exist a y such that whatever it is, that a finally returns 1. Whatever it is, we will worry about. So that's what I am trying to say. Don't start writing the code before the problem specification is written down. If x is composite, the requirement specification see, these inputs need not be integers, that can be arbitrary strings. I've just that's solved. Good. Well, I'll stop for tea now. So in a minute, tea has come. It's almost time, right? It's actually time. Okay, so just 5 minutes. Requirement specification for the verifier is, this is my verifier which I am going to design. Let's write down the specification. What is it? If x belongs to L, that is if x is a composite number, then for each composite number there should be a corresponding y which makes the algorithm return 1. Then for some y, this algorithm return value should be equal to 1. What is the next condition? If x is prime number, not composite means prime. So if x is prime number, then whoever is trying to cheat you into believing that this is prime, the algorithm should still catch. So but the point is, algorithm has to do some verification. You cannot trust the inputs and simply announce something is prime or composite. You should not allow the algorithm to get cheated by false. There should not be, there should not be false positives. That's the point. There can be false negatives. That means even if x is composite, if the certificate goes wrong, the algorithm may throw you out from logging in. That's fine. That happens very normally, right? But false positives are not accepted. That's what a verifier is supposed to do. So here, if x is prime, what is the requirement? For all y, then for all y your algorithm's return value should be 0. What should this algorithm do? Write down the algorithm. If x less than or equal to 1 or y less than or equal to 1 or y greater than or equal to x, don't accept.
What is y in this particular case?
Okay, what is y in this particular case? That's the question I want to ask. What is a certificate proof for compositeness? Huh? What should be, I'll come back. Yeah. What should be a proof for compositeness of a number? So a factor is good enough, right? A factor of the number is good enough.
For one is not prime. Number one.
Yeah. So in that case I can separately handle. If one is not composite, suppose, right? So then also I return. Then, so if x is less than or equal to 1, I return 0 because I don't have to return composite, right? If x is less than or equal to 1, I don't see. I'm only considering numbers which are greater than 1. So if something else is given, you return 0. It's not composite. Now what should I do? If x mod y, this is what I write percentage earlier, creating some problem for somebody. X mod y not equal to 0, return 0. If y doesn't divide x, then you return 0 because your certificate, even if the number is composite, your certificate is not proper.
So then, isn't this divisibility? Because I can take out.
Yeah, it's divisibility. That's another way of writing whether y is divisible by x. Then I will return. Now I return 1. If all other checks are clear, all checks are clear, then I return y. Is this a valid verifier? Let's check. Yes, because if x belongs 12, so let's look at an instance where 12, is 12 belonging 12? 12 belongs 12, right? 12 is composite. How will you make this algorithm satisfy accept 12? Provide 2, 3, 4 or 6. Isn't it? If you supply with 12, 2, 3, 4 or 6, the verifier outputs 1. Yes?
Here in the verifier problem, return 1 means that
Accept.
word means x is
1 is returned. Output is 1.
output is
1.
That means x is a composite number.
The algorithm return outputs 1.
No, here two problems are there. One is
No, see, verifier outputs 1. That's the only thing you should understand by return 1. Nothing more. This algorithm returns 1. Nothing more is nothing else is stated by return 1. The return value or the output value of this algorithm is 1. That's the only meaning of that statement.
but should satisfy this
No. It return 1 means this algorithm is going to output 1. Nothing more is it. Now, let's look at what this. Now I can independently ask the question, is this verifier good enough to verify this language? Is the verifier good enough to verify this language? See, the point is, the difficulty comes because we think in of everything in one shot. Verifier has a specification. Whether you write down an algorithm has a return value. These are two different things. Question is whether the algorithm's return value meets the specification of the verifier. So design the algorithm. The question is now whether this meets the specification. What is the specification of the verifier? Yes.
Isn't the second line redundant in algorithm? Second condition, if x less than or equal to 1.
Well,
That is taken care in the first line. Suppose if x is equal to 1, then first line says negative.
if y is something we give.
Suppose if x equal to 1,
No.
then first condition says if y less than or equal to 1 or y greater than
Okay. So this check is not required. Fine. Okay. So redundant check. Okay. Fine. Okay. So now does it make the requirements of a verifier for the problem? Let's see. What are the requirements? If x is composite, then, so that is why 12 is composite, for example. 12 is a language in input. Can you give me an input which is not in L? 13, yes. 13 is not in L. Now, can you make this algorithm return 1 on 12? Yes, provided as password you give 2, 3, 4 or 6. So that's a existence of one password is enough in case there are many. But not always. For example, 9 the only password is 3. Okay, but that's enough. For every composite number, just not for these two, for every composite number you can give a factor and make the algorithm return 1. So if x belongs to L, there is a way of making the algorithm return 1. For if x is a legitimate member of the language, there is a certificate or password which satisfies the verifier. Requirement 2, if x is not in L, that is if x is prime, or one case is already handled. So if x is prime, then whatever you give as y, the algorithm will only return 0. So there are no false positives. If x is not a valid user, is not a valid member of the language, whatever you supply as your candidate certificate, the algorithm's return is 0. So this algorithm qualifies to be a verifier for compositeness. So we'll break for tea. Yeah. Okay, so 9 and 2, it returns 0. So 2 is, so the thing is that if you give, 9 is composite, there exists a number which along with 9 if you supply it should accept, A should accept. Now 2 is not that number, but there are other numbers, 3 for example is there. So the existence of one certificate for membership in the language is enough. So let's start. So the notion of verifier is something fundamental because for very often there are lots of important and interesting problems where verification is possible in polynomial time, but actually solving in polynomial time looks nearly impossible. Why do I say nearly impossible? Because nobody seems to have a proof that it's impossible, but it doesn't appear likely. So there is a lot of industrial strength problems where it's very easy to design a verifier which runs very fast, but solving the problem, see the exercise set gives you a set of problems where verification is easier than solving but not substantially easier. See, you might go from 2n minus 3 to n or n square. So it turns out that on these problems the verifier is actually only marginally faster. But then you will come across the last problem where verification and solving are extremely different in terms of amount of effort required. So before that, let's try to formalize the notion of a verifier. So there are some technicalities involved, but let's start first, try to, once the basic idea is understood, I want to define, when does a language have a polynomial time verifier? Okay. So a language, an algorithm A is a polynomial time verifier. Again, this notion of time one should always be wary about, because it is not time, for a language L. So an algorithm A is a polynomial time verification algorithm for a language L if. This is what we want to define. There are a few things to be taken care of here. When I am talking about time constraints, right, there is a little bit of technicality, because I want to check whether x belongs to L. You say, okay, I will give you a proof, and then I realize that your proof is 1000 pages long, that reading the proof itself takes huge amount of time. So I need to say that if x belongs to L, if I want to verify the proof in polynomial time, I also have to put a constraint on the length of the candidate or proof that's provided. This is the additional technicality. Apart from that, things are very simple. So if there is an algorithm A is a polynomial time verifier for a language L, if, what is the constraint? For all x in L, this is just a technical notation, for each instance x where, or our notation was alpha, right? We can even stick on to that. For each alpha in L, so in that, to be consistent with the notation, I should write a set of all alphas is that alpha is composite, and then this should be alpha, this should be x. If somebody is confused, you should write this way, because our notation was, but I hope there is no confusion here. Okay, so I don't have to. So for all alpha in L, that means if the input alpha belongs to L, then okay, here there is a problem. I need to say that there exists a y of length at most polynomial in the length of alpha. Now, length at most polynomial in the length of alpha means what? I am going to fix a priori that, say for example, the proof can be of length at most length of alpha square or length of alpha cube or something like that. That's the maximum I am going to accept. Okay, so I am going to put a bound. If there exists an integer k such that an algorithm A is a polynomial time verifier for a language L if there exists an integer. So, I will need two integers. So, let me write integers, exist integers k greater than 0, c greater than 0, such that this is the technical part. Just forget about these numbers. It will be clear in some time. But if there exist integers k and c greater than 0 such that, forget about this k and c for now. What is the requirement of the verifier? If alpha belongs to L, then there exists an x such that A alpha x evaluates to 1. That means on x and alpha the algorithm gives you 1. Now I put that k constraint. I want to say that there exists an x such that x, the length of x is bounded by length of alpha raised to k. So, I am trying to say that if x belongs to L, there is a proof which is not very long. There is a proof x or a candidate x whose representation does not require too many, the description of x itself should not be very large in as compared to the description of alpha, such that when your algorithm is applied with alpha and x, it runs and returns 1, correct? The proof is verified and you said okay, x belongs to L. So, if x belongs to L, there exists at least one certificate which is short such that this algorithm accepts x along with the appropriate certificate. Is this clear? What is the other requirement? If alpha does not belong to L, then for any x, whatever you supply as password, here I can drop the constraint. I do not care about the length of x. The reason is if see one, I know that if there is a valid proof, the proof has to be at most of this length. So, the first check I check is whether the proof is exceeding this length. Immediately I can say okay, otherwise I will reject. So, that is, I do not have to write for all proofs of length up to this. I can make every proof. If alpha does not belong to L, I can design the algorithm so that it rejects all fake proofs or false positives. Okay. Then what else? So, this is the requirement for a verifier. Where is that polynomial time coming? A runs in the complexity, the time complexity of A of the algorithm A must be order of length of alpha plus length of x raised to c. So, for some constant, the running time should be bounded by some polynomial, that is all. The polynomial should not change with the input. See, I should fix the polynomial and say okay, this is the given the input, the proof can be at most n cube. If k equal to 3, then I say that okay, if the input is of length 100, the proof can be of length at most 1000, because n cube, 10 cube is 1000, 100 cube is whatever. Okay. So, this formal definition very clear, take your time. So, this is nothing but the definition of the verifier we stated above, added with one or two constants here and there to ensure that the proof is bounded, the length of the proof is polynomially bounded in the length of the input, that is one constraint, and running time of the algorithm is also bounded polynomially in the size of the input. Is this very clear? Is this very clear? We will design algorithms for this, but let's come back to this question. Is this verifier a polynomial time verifier for compositeness? Yes.
By any chance, C or K anything have any connection between them, or it is random to?
See, you can put max of, you can make it one constant saying that, see, we'll take the larger constants and make it one constant, so everything is possible. So that is not important. It's only thing is, what matters is that the length of the proof is bounded in by some polynomial. The proof's length given alpha, you cannot, your algorithm will not accept candidates of very long candidates. That's one constraint you put, and the algorithm's running time is also bounded. Beyond that, these numbers, it can be any numbers. There should exist some numbers, that's all it says. Okay. So you can get rid of one constant, all kinds of things are possible. But these numbers are not important. It's only that there should exist some numbers. That's all. Now take a minute to digest this definition. This is actually very little more than what has already been done. Yes. Pardon? Okay. So given an algorithm, you know the notion of time complexity, right? How many key operations are done as a function of n? That function by some n raised to length of, see, if n is the input size to that algorithm, then it will have some time complexity t of n. T of n by n raised to c ratio should be bounded. That's all. So time complexity is order of n raised to c means the algorithm's time complexity divided by n raised to c must be bounded. See, time complexity is of an algorithm is polynomial means there is a polynomial, say n raised to c, such that time complexity divided by n raised to c is bounded. That's all.
So how we represent the constant
No,
and c is greater than 0?
No, it doesn't matter. See, all I am trying to say is these things are bounded. The permitted length of this proof is bounded by some length of this into some polynomial in the class. It doesn't matter what constants these are. That's what I am trying to say. There is see, the proof cannot be too long. That's all it says. Okay. For the time being, at least, don't worry too much about this. These are just technical constraints. It's just saying that the verifier is not expected to accept proofs beyond a certain power of the length of the input itself. Okay. Similarly, the verifier is not expected to run, should not take too much time to run. That's all.
So in verifier, there are two inputs.
Yes.
Alpha and x. That's why we are taking the sum.
So that is input size is the sum. See, there are two inputs, then the size of this input plus size of the input is the n.
That's why.
That's all. So this is your n. See, the input size, once you fix the input size, you know T of n. T of n by n raised to c should not go to infinity, that's all. Even for any value of n. Or it should not go to infinity as n becomes large, that's all. So the time complexity of A must be this. Okay, that's a constraint. The length of the proof should be bounded. That's a constraint. Is that okay? Okay. So let's try to look at the next problem in the problem set. Okay, there are some technical definitions. Before that, I will finish this theory, then we can look at the problems. Okay, so when do you say that a language is in NP? When do you say that a language is in NP? If there is a polynomial time verifier for the language. A language definition. A language L is in NP if you can design a polynomial. See, I have already written down what is a polynomial time verifier, right? A language is in NP if there is a polynomial time verifier for it. Pardon? There is an equivalent characterization for this class in terms of non-deterministic Turing machines, which I am not going to pursue here. This is an equivalent way of defining it, which avoids Turing machines. So L is an NP if there exists a polynomial time. There exists a polynomial time verifier for L. Okay, so now let's start with the problem set, but let's first define. So this is straightforward, right? Okay, so again remember, NP is what? What are the members in NP? Each member of NP is a problem. NP is a collection of problems. It's a collection of languages. So NP is a collection of okay. So is there any connection between P and NP? What? If a language is in P, it is also in subset of, it is also in NP. Why? See, if you have an algorithm that solves a problem in polynomial time, forget about the certificate. Even ignore the certificate, solve it, say yes or no, right? See, you have a, if you know how to solve X belongs to L in polynomial time. Okay, so suppose, so Clive, suppose L is in P, then L belong to, is this enough? If L is in P, then L belongs to NP. This is what I want to show, right? Right? So suppose L belong to, okay, if how will you prove this? So what is given? What is to be proved? Just a minute. If any algorithm is polynomial time, it has no bearing with, see, where does L come into picture? Okay, so assume that, proof. Let A be an algorithm that accepts L in poly time. Why am I permitted to make this assumption? What is given to me? What is given to me? So I am trying to prove this theorem, claim if L belongs to P, then L belongs to NP. That is every problem in P is also in NP. P is a subset of NP. How will I prove this? So let L be a language in, so let proof, so given L belongs to P, to prove that L belongs to NP. This is what you want to show, right? So I assume that let A be an algorithm that accepts L in polynomial time. Why should such an algorithm exist? By definition, L is in P means there is a polynomial time algorithm for it. So now look at the following algorithm. B. Okay, what should I construct? A verifier for L. Then I will show that polynomial time verifier for L. That will show that. Show what? L belong to NP. So here is what. Run A will return 0 or 1, return that value. Does it work? See, this is a function. What is this code doing? It takes two inputs. Okay? It takes the first argument, calls A with that argument, and whatever is returned by A, see, if A returns 1, you output 1, if A outputs 0, you output 0. Is that clear? So this function is doing what? I know that there is an algorithm A that accepts. What is the input to L? A and a number x or a string x, and this A will determine whether x is in x. What is A going to do? Check Ax is equal to 1 if x belongs to L, isn't it? A is a polynomial time distinct algorithm for L. That means if x belongs to L, A returns 1. If x doesn't belong to L, A returns 0. Now what is this algorithm going to do? It is going to take an x and a y as input, and then it simply calls A. Whatever A returns, this guy will return. Now does this algorithm B satisfy the requirements of a polynomial time verifier for L?
Whenever alpha belongs to L,
Yeah, so again I have written x and y, so let's have x and y. So if x belongs to L, well, this is very simple because the requirement is there exists a y for which axy is axy equal to plus bxy equal to 1. Here for all y, bxy equal to 1. Whatever be the y, this guy doesn't even check the password because it knows how to verify the user directly without looking at the password. So if you know the user, you don't have to look at the password, right? If you can solve the user in polynomial time, you can identify the user in polynomial time, the password you can ignore. That's what is happening. And now if x doesn't belong to L, if x doesn't belong to L, see, because this guy is already robust, I have a person verifier. I don't need a, see, my verifier is just, there is somebody who can identify people correctly. So my verifier algorithm simply ask the user, okay, give me the password also. I throw the password into the dustbin and ask this guy to verify and then let the person in. That's what is happening. So if you can solve a problem in polynomial time, then trivially you can verify it in polynomial time. Is this clear? Is this clear? So what is the consequence of this? See, if you look at the world of all problems, now these are the languages in polynomial time. So there are several languages, L2, L3, L4, etc. here. There could be somebody here, L5, L6, L7, L8, etc. here. Now, one thing is clear, anybody here, this is a larger class. Now, whether these people can be brought here is open. That's an open question. Nobody knows. Okay. So, that is a P not equal to NP problem. So, what we know is, so Bxy is always 0. So, B is a verifier. Why does P run in polynomial time? Because A runs in polynomial time and your constant Y doesn't matter because you don't even look at Y. So, forget about the constants. Time is polynomial because A runs in polynomial time, everything is done. So, B is a polynomial time verifier for from this we conclude that L belongs to NP. So, this is the picture. Anything in P is also in NP. The other way it is not clear. And that is our business, to see what is to be done when somebody, you find somebody here. So, your research advisor gives you a problem which doesn't, you are not able to put it here. See, the professor asks you to show that this problem has a polynomial time solution. After 2 years of work, we are not able to do this. Now, what are we going to do? That is what NP completeness is about. So, essentially the idea is, I have a list of huge, big names in the field, big problems which are already known to be very hard to solve. What I show is, okay, if my problem has a polynomial time algorithm, all these problems also will have polynomial time solutions. So, that is the kind of strategy about NP completeness. We will see this later. So, now before I get to the problem set, I will just introduce a few graph problems. Now, so far there has been little of graphs, right? So, let us introduce a few graph problems. But is this clear? Is this clear? NP minus V, whether it is non-empty itself is not known, right? Okay. Okay, we will introduce that graph problems maybe tomorrow. So, the problem set is already uploaded where it is defined. There are a few problems like vertex cover, independent set, click, etc. defined. We will start with this tomorrow. So, now we will get back to the problems. Write the last problem. So, the last problem asks you to, see, listen, the last problem is the following. Everybody knows what a Boolean formula is, isn't it? X and Y or X, not X and Y, kind of conjective normal form Boolean formula. Okay? So, the question is whether there is a truth assignment that satisfies the Boolean formula. Now, the question asks you to show that this problem is polynomial time verifiable or this problem is in NP.